new knowledge. Thank you so much.
Thank you, Professor Reddy, for your very kind introduction. And thank you for this invitation. And thank you to all the delegates for attending this webinar. It is my great pleasure to make a presentation, although it's online, but it's a very exciting situation to make a presentation in front of many people, more than 100. Okay, so I titled my lecture Marginal Soils because I have been working with several unwanted soils these years. For example, naturally contaminated soils, recovered soils from disaster waste, or nuclide contaminated soils. And management of these unwanted soils, or we would say marginal soils, has been a significant geoenvironmental issues. And yes, if we have plenty of spaces and plenty of money, we can dispose and landfill all of these soils, but we have limited resources and limited land spaces. So therefore, environmentally acceptable and proper utilization is expected. For example, in the country, we have almost 300 million cubic meters of excavated soil generated, which includes the naturally contaminated soils. And 2011 disaster, we had a huge amount of disaster waste, including almost 10 million tons of recovered waste soils. And we also have 30 million tons of the nuclide contaminated soils due to Fukushima disaster. So these soils are the issues we have to take care of. So today we have limited time, so I do introduce only 2 of 3 naturally contaminated soils and recovered soils from disaster waste. Okay, so let me go on our first marginal soil, which is the excavated soils with the geogenic contamination. In the country, our national government collected the statistics for almost every 6 years since 1996, which is followed by the strategic plan decided by the government. And according to this census, which was collected in 2018, the 80% of the surplus excavated soils are used at either the same construction site or different construction site after the transportation and sometimes improvement. And we have the system to connect the information regarding the generation and reclamation in a regional basis to create better connections. However, we have several problems. For example, geogenic natural contaminations might have been discouraging the use of such excavated soils. And sometimes illegal dumping has been causing the serious problems. For example, 2 years ago, we had the serious debris flow in nearby the Fuji Mountain due to the heavy rain. But not only the heavy rain, but also the improper soil dump was considered a trigger. So people started to aware that the proper soil management to monitor the transportation and reclamation of the soil is required. So the location is called Atami City. So if you type 2021 Atami landslide in YouTube, you can find a serious debris flow which killed more than 20 people and the top of the debris flow was the improper soil dump, which was considered the surplus soils transported from other places. So our government has decided to make something, and our law on the soil embankments was immediately amended less than 1 year, and now already effect in this May this year. So this is the situation of the soil management. So as I mentioned, proper soil management is required, but also as I mentioned, the geogenic or natural contamination might discourage the reuse of the soil materials. You might know that the soils containing the arsenic, lead, etc., are widely distributed not only in this country but also all over the world. For example, in the marine clay or silty layers, mudstone, or hydrothermally altered layers, or all the embankments which are coming from a marine clay or hydrothermally altered geology, or reclamation using dredged soils. So some soils generated through the excavation works at the construction sites exceed the regulatory standards for the leaching values of the arsenic, lead, fluorine, boron, selenium, etc. And we have a regulation decided by the Ministry of the Environment, as well as the technical guidelines by the Ministry of Land Infrastructure and Transport, has been encouraging the use of such soils and the proper management like this encapsulated embankments. Sometimes people are rather too conservative to hesitate the use of such soils, and sometimes people are using these soils without the proper care. So we have to be in the good balance for the utilization as well as environmental management. So that's the situation of the general geogenic and natural contamination. This is the arsenic and lead distribution collected by our national research institutions, which we call ICE, National Advanced Industrial Research Institutions, Science and Technology. And these maps indicates the distribution of the arsenic and lead. If you search the web page of these research institutions, we can find the distribution maps, not only arsenic or lead, but also other, almost all the elements. And if we look at these two elements, you can find that there are some places which have rather high concentrations of the arsenic as well as the lead. So we can recognize that the existence of the arsenic and the lead in natural geology is the common issue. And this is not only the Japan local issue, but also the universal worldwide issue. And this is the map cited by the one professor, introducing the arsenic affected ranges. You can find that there are many places which are affected by the arsenic in groundwater. So this map is focusing on the groundwater, and I do focus on the soils, but they are close. so we have to be careful about this situation. And if we look at carefully about the concentration levels of these arsenics, it depends on the situation. For example, our colleagues have has collected the data of the arsenic and lead concentrations for the marine clay in the Osaka area. You can see these graphs. The x-axis is the concentrations normalized by our regulatory limits, which is 0.01 milligram per liter as the leaching value. We have rather special national leaching test method in which we put soils, 100 grams of soil, so with the 1 liter of the liquid. So the liquid per solid per liquid ratio is 0.1 or 10. And after the shaking and filtration, we determine the concentrations of the target elements in the liquids. So this is not the total concentration of the elements in the soil. This is just a leaching value from the soils. But you see, for the arsenic, we have this is the regulatory limits. So we have several marine clays which exceeded the regulatory limits. But you see, the highest value is almost at the 12 compared to the regulatory values, not like 50s or hundreds. And if we look at the lead, the concentration levels are much lower compared to the arsenic. Almost all the marine clays are less than the 3 times larger than regulatory values. Regulatory values. So we'll say, yes, we have the soils, marine clays exceeding regulatory limits, but most of the soils only exceed 10 times higher for arsenic or 3 times higher for lead than the regulatory values for leaching. So from these results, we can believe that it should be manageable. That's the basic situation. But of course, there are different types of soils or rocks, particularly specific rocks might have much higher concentration levels of arsenic or lead, but mostly the geogenic contaminations do not have the too high concentrations. So therefore, our governments or private sectors or research institutions try to promote the utilization of such soils with geogenic contaminations. So our first option has been a containment using a geomembrane or sometimes a clay layer, which has been widely applied. And yes, this has been widely utilized, but sometimes a stability issue exists, particularly for the slope side. And sometimes we do the sufficient compaction to minimize the infiltration. As a result, the leaching value might be minimized and effects into the groundwater might be minimized. But it seems like the no countermeasures. Of course, it is sufficient compaction is a countermeasure, but public acceptance sometimes exists. So therefore, recently we have been working with the attenuation layer either artificial or natural, in which we have the natural original ground or artificial attenuation layer below the soil with a natural contamination. And for this, we can conduct a compaction, sufficient compaction, and also if we have a sufficient sorption or attenuation capacity in this attenuation layer or natural layer, we can solve the problems with the natural contaminations. But for this attenuation layer method, we have more precise evaluation of design compared to a geomembrane method. For example, the leaching value, leaching situation, leaching behavior should be carefully studied to decide the material and the thickness of the attenuation layer. Okay. So for considering the leaching values, we have to consider the factors affecting the leaching of the heavy metals or metalloids from the soils and rocks. For example, particle size and surface area, soil density, which might influence the hydraulic conductivity and infiltration. And duration is also an issue which might change the chemical situations, for example, ORP or pH values, and exposed or covered, and groundwater levels. So these factors might affect the infiltration, permeation, saturation degree, dry and wetting conditions, and chemical properties. And as a result, leaching might be affected. So in our country, current regulation is based on a simple batch leaching test, which does not consider the above factors. The more appropriate evaluation method is required. The crushed or not, or batch or column, or how long, or how to consider the oxidation and reduction conditions. So I'm sorry that I do not prepare the slides for these issues, because these issues might require the very precise researches, and many researchers have been working on this. So you can find the individual publications to learn more about these aspects. But I would like to only mention that the one very significant phenomenon, which is oxidation. If we have the pyrite minerals exist in the soils or rocks, the oxidation processes occur with the presence of the oxygen and water. We might have the very high arsenic conditions. The arsenic acid condition. And if we have acid condition, this acid condition might increase the leaching of the heavy metals or metalloids. So if we have our soils which have the pyrite minerals, and if they are buried under ground, no exposure to the oxygen or water, so the acidification will not be occurring. But once excavated, they are exposed to the oxygen and the water easily. Also, therefore, so the oxidation, acid drainage, and leaching will be occurring. So this is the very important mechanism we have to consider if we work with such natural contaminations. And there are various types of the elements which might exist in different ways. For example, if we look at arsenic, arsenic exists with pyrite minerals, or arsenic exists with the ferrum oxides. So they behave differently. For example, this one, the leaching was occurred by under the oxidation process. And this case, leaching is occurring at the reduction conditions. So they behave very much differently. So we have to make sure what types of the arsenic, or what types of elements exist with what types of the other chemicals, and these soils and rocks formed how and where and in which conditions. So these issues should be considered carefully. So what we have been working with these naturally contaminated soils. We have been working with the attenuation layer method because as I mentioned, concentrations of geogenic contaminants are not necessarily high. So excavated soils may not be necessary to be fully covered by a geomembrane. And if we have attenuation layer which has a sufficient capacity to trap the elements of concern from the excavated soils, this might be the cost-effective method. But we should consider two issues: leaching behavior and attenuation behavior. So to enhance the attenuation performance, we sometimes use the enhanced materials, and for example, the MgO-based material, it has been widely used in this country to mix with host soil to create attenuation layer to enhance the sorption capacity. Okay. So the first issue, which is leaching, as I mentioned, our regulatory method is the simple batch leaching test. But for the design of the attenuation layer method, we recognize that the simple and single batch leaching test may not be sufficient. So our group has been conducting the numerous numbers of the column test with the naturally contaminated soils, and try to find the tendencies depending on the elements, or depending on the types of the soils and rocks. For example, this is the leaching behavior of the selenium and boron, in which you see the monotonous decreasing of the leaching values found. So for such elements, we should be careful about the first few weeks, or first few months, or first few years. But for the arsenic, for this case, we have the higher concentration values at more than 1 volumes of flow. So which might occur 1 year later, or 2 years later, or 5 years later after the filling of the embankments. So we have to make sure that our embankments how long it will take to get such peaks, comparing our column test results. But it might be difficult, so we might use the highest values for this or for this for the design. But yes, and sometimes we have the leaching concentration values from a batch test, which might be utilized for the design. Okay, so we have to make sure that the behavior of the leaching values, depending on the types of the elements, like them, or types of the soils or rocks. And this is the one example of the sorption performance against the acidic conditions. As I mentioned, some soils and rocks will be changed to the acidic conditions. So for our test, we prepared arsenic simulated leachate with the pH values of 2, 4, 6. And yes, we predicted that pH 2 should have rather severe conditions if we have only a sandy soil as attenuation layer. But if we have stabilizing agent to enhance the attenuation and sorption performance, you see all the cases they satisfy the allowable regulatory limits in this country. So yes, we have to study more about the durability, but we might have the potential to use such stabilized agent to create the attenuation layer, and we have a potential to encourage the naturally contaminated soils utilization by using attenuation layer method. So this work is still on the process, and further researches are necessary. For example, leaching behavior, how to model the leaching behavior for the design, and how to predict the chemical status, chemical situation in the embankment. For example, usually we test the soils and rocks at the laboratories, and mostly our soils and rocks are exposed to the air and oxygen and water. But sometimes in the embankments, very high embankments or very type of filling site, the oxygen supply might be minimized. So the reduction condition might occur. So the such chemical status in the embankment should be considered, and how to predict the chemical status on the leaching behavior has been an issue, and many of the researchers in Japan has been working on this topic. And how to decide and evaluate attenuation layer material, and we have to standardize the testing method because we do not have the standard universal method to evaluate the attenuation performance. After that, we decide the thickness of the attenuation layer, but usually we draw our embankments like this, but sometimes inclined base, sometimes the inclined from both sides, or sometimes we have different types of soils. So 3D dimensional effects should be considered, not including the heterogeneity and preferential flow. So even the heterogeneity or preferential flow exists, our attenuation layer should be reliable. So this is another challenge to implement the attenuation layer. Okay. So let me go to our second marginal soils, which is the recovered soils from disaster waste. We have been working on this topic because of the huge earthquake and tsunami occurred in 2011 at the Tohoku region, Japan, east coast. This is the tsunami disaster, which transported seabed soils in the ground. And for the 2011 East Japan earthquake occurred March 11, 2011, with a magnitude 9.0, and tsunami, 40 meters maximum run-up height, and more than 500 kilometers flooded by tsunami. So we had almost 3 million tons of the disaster debris. So if you're interested on this topic, please look at this publication in which we have summarized the geoenvironmental issues caused by the 2011 East Japan earthquake and tsunami. Okay. Regarding the disaster waste treatment, the large amounts disaster waste are generated as the mixture of various types of materials, but actually 1/3 of them was the soil fractions, and also 1/3 of them concrete fractions. Okay. And our government has decided to conduct a separation, incineration for vulnerable fractions, and the reuse of these separated materials, and completed in 3 years in most places. And most of the separated materials had we had experiences, but the recovered soils from disaster debris, we did not have such experiences. So it was a big challenge, use of the recovered soils in reconstruction works, and finally successfully conducted. But we have another anticipation on the future larger earthquake, which will be occurring in the next decades, which called the Nankai megathrust earthquake. So we have to prepare for the future larger disaster. So what we have done for the disaster waste is that these are the waste soil mixtures, the crushing and the separation using the equipments. We recover the soils from waste fractions and use in embankments. And these are the compaction curves which we have conducted at the early beginning of the recovery stage. And you see very high dry density with the good compaction properties, while we have poor compaction properties from the waste dominant stockpiles. So we recognize that we have good soils. We have good soils from disaster debris. So if we recover the soils properly from a disaster debris, we can utilize these materials for the reconstruction works. So efficient removal of a waste fraction is required. So we have been working on the efficient removal. So we use these laboratory equipments for separations. This is the rotary screen with the opening size of mesh is 20 millimeters, and vibrating screen with the mesh over 20 millimeter of opening sizes. So we try to clarify the factors affecting the quantity and quality of the soils recovered from soil waste mixtures. Well, these are the laboratory experiments. So we use the simulated materials, and we prepare different soil types, different water content, and we prepare different soil separation machines, which are rotary screen and vibrating screen. We have also conducted a pilot scale test for the separation of soil waste mixtures. This is the very big rotary screen, but with the same opening size of a mesh. And this is the vibrating screen. We prepare the simulated soil waste mixture. This is the overview of the pilot scale test. So let me introduce some of the results. We prepare the simulated soil waste mixture by using the soil and wood chip. So before sieving, we have soil waste mixtures. After sieving, we have residual materials over the sieves, which are the residual wood chip and residual soil. We also have past materials, past wood chips, and past soils. Ideally, we would like to have the pure soils here and pure wood here. But eventually, we have residual soils over the sieves and past wood chips. So we have carefully checked the remaining materials by scraping in water by hand. Okay, so let me introduce some of the results. These are the results of the passing amount through the sieves with the different fine contents, pilot scale, and laboratory test with different water contents for rotary screen as well as the vibrating screen. So we have a very similar tendency for these two different screen types, but rotary screens might show the better separability because they collected more passing amount. Because we prepared I don't remember exactly, but 90% of the soils prepared in our soil waste mixtures. And we have a similar tendency for these two screens. Percentage of passing decreased with water first, and then increased with water. because we can imagine that if we have the specific amount of water, the soil waste mixture will become very sticky, so difficult to separate them, difficult to separate them. So we have this tendency for both cases, and we can easily recognize that the higher fine contents lead to the worse separability due to the higher water retention. So these are the situation of the materials. And yes, over the screen we have residual materials, and below the screen we have past materials. If we focus on the past wood chips, which is the quality of the recovered soils. If we have a large amount of past wood chips, the quality of the recovered soil is not good. So we are sorry that we do not have a clear trends either with the water content or types of a screen or the fines contents. But with the fines contents, percentage of wood chip was slightly lower of 1 to 6 percentage. Okay, and we try to summarize our results, the preferable conditions, because we had better to recover the soils, the more in terms of the quantity, and for this, and also we should consider the quality of the recovered soils, so less past wood chips. So we plot all our results with the soil recovery rate, which is the residual soils versus past soils, as well as the y-axis of a percentage of wood chips, which is indicating the quality of the recovered soils, quantity of recovered soils. So we had better to have this range. So for example, if the 40 and 50% water content, 10%, we had the best condition. That means the rather dry condition is necessary for better separation efficiency. We also found that the effects of the soil types, if we have a clay-rich soil waste mixtures, rotary screens might be better, while soil-rich disaster waste, soil waste mixtures, vibrating screens might be better. So if we have a tsunami disaster, rotating screen might be better, and we have river flood by heavy rain, vibrating screens might be better. But these are just the beginning of the researches, and further researches are needed for to see the situation of the various cases. Also, we should look at the separation mechanisms to generalize our results and create the better design method. Okay, so let me conclude my presentation. In my presentation, I introduced two different types of marginal soils, geogenic naturally contaminated soils generated through excavation works in construction. The soils recovered from disaster debris, and these utilizations are encouraged to reduce the soil disposal, but require geoenvironmental, geotechnical, environmental, and sometimes sociological challenges. And there are several countermeasures which have been implemented to use naturally contaminated soils. And we have been working on attenuation layer method, which is expected to be the effective method from a geotechnical and environmental viewpoints, but requires further researches for proper implementation. And use of the recovered soils from disaster waste was successfully conducted for the recovery of a 2011 disaster and contributed to the prompt disaster recovery. But further efficient separation is required, and we have been working on this issue to see the various cases as well as the separation mechanism to prepare the further catastrophic disaster. Okay, this is my last slide. Acknowledge the individuals and institutions, but not only these individual institutions, but also there are many individuals and institutions helped our work. So I thank all of them. And I thank you very much for the listening my presentation today. Thank you very much.
Yeah, thank you so much, Professor Katsumi. So a very excellent presentation and very useful to many attendees. I know some of the attendees personally and what they work on. I think some of the things that you showed on leaching experiments and leaching assessment, that would be really useful for people working on beneficial utilization of industrial products, waste materials, and other things. And the second part that you talked about, like a soil waste mixture separations, that's also very relevant in India. There are a lot of landfill mining is going on, and then separation of the waste fractions and the soil is a very important issue. I think some of the research that you have done could be exactly replicated to evaluate the landfill mining materials in India. So there are a lot of interesting ideas that you have given through your research projects that other people could use and study the problems that they have in their locations, in their places. So thank you so much. I mean, your slides were very, very good, and your explanation is extremely good. So I let our attendees open, type your questions in the chat box or unmute and ask your questions. So if you want, Professor Katsumi, you can stop sharing the screen so that everybody can see you, and you can also see. And see, I request attendees to put your questions in the chat box, questions or comments, and also, if you want to unmute and ask the questions, that's also fine. So let's go with one question.
I,
Yeah, anybody